Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 32 on simple volumes.
In this lesson, we'll progress from computing areas in 2D to computing volumes in 3D. Following the pattern that we used with areas, we'll begin with some of the classical shapes and consider their volume formulae. We'll look at round balls, cones, and pyramids.
When computing volumes, there's really only one formula you need to know, and that is that the volume is the integral of the volume element, and all of the difficulty lies in finding the correct volume element. The simplest example would be that of a rectangular prism of length L, width W, and height h. In this case, computing the volume element is simple if we slice along one of the three principal directions. One volume element might be W times h dx, integrated from 0 to L. Another, L times h dy, integrated from 0 to W. Or finally, L times W dz, integrated from 0 to h. All three integrals return the volume, length times width times height. For a less trivial example, consider a cylinder with base, a disk of radius r, and height h. There are several ways to compute the volume, as pi r squared h. One method involves taking the associated area element for the base and multiplying by the height of the cylinder, h. As we saw in a previous lesson on area, there are several different ways to do this. We could use a lateral slice of thickness dx and obtain as a volume element 2h square root of r squared minus x squared dx, integrating from negative r to r. If instead we use an angular wedge, then we integrate with respect to theta, the volume element, 1/2 r squared h d theta. Here theta goes from 0 to 2 pi. Finally, if we use an annular area element, then associating a t variable to that, we consider as a volume element this cylindrical shell whose volume is 2 pi t times h dt. Here we integrate from 0 to r. Now moving up in complexity a little bit, consider a round ball of radius r. In this case, we're going to slice along a lateral plane. This leads to a disc-shaped volume element. But as we slide the plane back and forth over this solid ball, we see that the radius of the disk changes. It's going to take a little bit of work to figure out this volume element. In this case, since it's always a disk, the volume is the area of that disk, pi times whatever its radius is squared, times the thickness. Let's call it dx. Now, at a particular value of x, what is the associated radius? It will help to build a right triangle in a cross-sectional view whose base is of length x, whose radius is, of course, r. What is the height? In this case, it is square root of r squared minus x squared. So to compute the volume, we integrate the volume element. That is, we integrate pi times quantity r squared minus x squared dx, as x goes from negative r to r. In contrast with computing the area of a round disk of radius r, computing the volume of a round ball of radius r is relatively simple. This integral is very straightforward, yielding pi times r squared x minus 1/3 x cubed. Evaluating that from negative r to r leads, with just a little bit of algebra, to the familiar formula 4/3 pi r cubed. There's more than one way to derive this volume formula. Let's look at a different method. Consider slicing up the ball into cylindrical shells as a volume element. Let's choose a radial variable. Let's call it t. And then consider a cylinder that sweeps out the volume of the ball parallel to some, let's say, vertical axis. In this case, what can we say about the volume element? Well, I claim it is 2 pi th dt. That is the area of the annular strip of thickness dt and radius t times the associated height h of the cylinder. Well, that's great, except what is h? It depends on t. Again, building the associated right triangle is going to help us out. This triangle in profile is going to have hypotenuse, r, the radius of the ball. The base is of length t, the radius of our cylinder. The height is given by Pythagoras as the square root of r squared minus t squared. But that's the height of the triangle. The height of the cylinder is this doubled. Hence, our volume element is 4 pi t, square root of r squared minus t squared dt. And to compute the volume of the ball in this alternate fashion, we integrate this volume element as t goes from 0 to r. Now, this is not so difficult of an integral. It's not quite as easy as the last one, but a simple substitution, letting u be r squared minus t squared. We see that du is negative 2t dt, and that we can rewrite this as the integral of negative 2 pi square root of u du, as u goes from r squared to 0. That integrates simply to negative 2 pi times u to the 3/2 over 3/2. Evaluating from r squared to 0 and simplifying the algebra leads to 4/3 pi r cubed. A last method for decomposing the ball and obtaining the volume would be to use a spherical volume element. This is a round shell, concentric with the ball. We're going to need to choose a variable to denote the radius of this shell. Let's call that rho. That's a letter that you'll be seeing again in multivariable calculus. In this case, I claim that the volume element is really the surface area of this shell, 4 pi rho squared, times the thickness, d rho. Now, I'm not going to justify that computation other than to demonstrate that when we integrate it, as rho goes from 0 to r, we obtain most simply 4/3 pi rho cubed. As rho goes from 0 to r, we have very easily the formula for the volume. Using this spherical shell seemed to be the simplest integral. But determining what the volume element is in terms of the surface area of that shell was maybe not so simple. The moral of this story is that the proper volume element can make the integration very, very simple.